So let's continue with our steady state building load calculations, and for this video we are going to go into more details of the transmission load, which I said earlier in the introductory video, right? So let's look at the transmission loads. And it is also the same as conduction load, because as I said in the earlier video, that's the transmission from walls, basically the envelope. We'll group them all into the envelope, building envelope. So the walls, floor, roof, and we'll also include the infiltration. And how do we include that? I'll discuss that in this video itself. But it's also the conduction load. So the conduction load basically is calculated using Q, which is the amount of heat transfer happening, is equal to K A into delta T over delta X. Over here we are going to little modify it, and we'll use the expression for overall heat transfer coefficient. So this is the conduction coefficient which we have. That's the conduction coefficient. None of these are working or what? Okay, this is working. This is the conduction coefficient. But if we want to use the overall heat transfer coefficient, which is much more easier, because when we are going to combine the heat, infiltration load, roof and all, it's not easy to get all values of K for infiltration, let's say. Hence, instead of this expression, we are going to use another expression, which is UA delta T. And why so? This expression is complementary to the Newton's law of cooling, where our U is overall heat transfer coefficient. Right? And the unit for U, let's just put down all the units over here. So the Q unit will be W, Q dot. It's a heat transfer rate. It's always the rate of heat transfer which we are going to care about. It's not the amount of heat anytime in our module. So it's the watts, or let's use the word or, it might confuse. So or BTU per hour. That's the other imperial unit which is prominent in USS specifically. The U into A, that's the single factor which we are going to consider most of the time. And the U and A combined will have units of watt per degree Celsius, or BTU per hour degree Fahrenheit. The U expression individually would have watts per meter square into degree Celsius in the denominator, or BTU per hour per feet square per degree Fahrenheit, right? And the temperature we are going to use over here in the SI unit, it's degree Celsius or Kelvin, and in imperial units it's going to be degree Fahrenheit. For some instances, for some calculations, we need to use degree Rankine, and wherever it comes, I'll mention that thing specifically for your understanding. Now let's continue with our conduction heat transfers because of the transmission. So as I said, it's because of the walls, roof and floor and the infiltration. Let's look at the first three. For the first three, we want the values of U, A and delta T. The delta T is very simple, so let's just expand this formula. U into A into delta T means either it could be T in minus T out, or it could be T out minus T in, it depends. It will just change the heat gain or heat loss. It could be heat gain. It's heat gain if so it's going to be heat gain or heat loss. From where? From the envelope. From the building, it's for the building it's going to be heat gain, or from the building it's going to be heat loss, depending on the T in and T out. T in is the set point temperature or the inside temperature of my building. So for T gain, the T out should be greater than T in. That means if outside temperature is higher than the inside temperature, that means inside temperature is lower. That means I want to keep the building cool. That means we are getting heat from the building from outside and we want to keep it cool, so we'll use the air conditioner or the cooling system of our building. For heat loss, it's going to be T in, which is greater than T out. That means my outside is cooler and we want to keep the inside warmer. Hence, we want to the heat is lost from the building, and to compensate for that loss from the building, we need to keep in and add more heat to the building. Understood? Now let's continue with the U into A expression. So U will get A, we need to get A from the measurements on the building. We can physically visit the building. So it's a physical visit, or we can use Google Earth, Google Maps or Google Earth to get an estimate, because they have a scale, if you remember. The third very important thing is you can look at the directory or repository of your institution, because I study at Texas A&M. They have a complete repository of all the building dimensions. Exactly, they have the areas, gross area and all, building area, gross area, construction area and everything. So we can get a basic estimate. We'll not definitely get the individual areas of walls on each direction, which is required for UA calculations now, but we can get a basic idea of how much our physical measurements are correct or not. And the U value we need to use based on standards, ASH, RAE standards, or the second option is measurements again. Now let's look at these things in more detail. So for each of the walls, floors and roof, what we want to do is, let's take it the wall. So if we have a building like that, let's say there are some windows there, some doors there. Let's say these are the windows. Let's say this is the glass area in common, because windows or walls, windows or doors, doesn't matter, it's the wall glass area, and it's not considered in our calculation for transmission conduction load, because we'll take it separately later in some other ways. Okay, so and let's say we also need the direction. So the procedure to solve for conduction load will be, we need some direction, north, east, west, south. So for each of the walls, so this wall maybe is in standard south direction, so we have north, east, west, south. The building could be oriented in other way, and it could be northeast, northwest, southeast and southwest. This could be a possible combination, this could be a possible combination, and there could be some other also. It completely depends. Now our task is to find the areas, area of wall in north direction. So the wall which is facing north, let's say this is the wall which is facing north in this direction. Then I want to find the total area of the wall. That means the opaque wall only, not the total area. That means I'll take out the total area this much and subtract the area of the glass. So I'll get the area of opaque wall in each of the directions. It could be northeast direction, also north direction, whatever. It depends on the building orientation. But we need the area that's coming from the physical measurement, which I said earlier. For each of this direction, each of the walls which we have, it could be a 5-sided building also, and there it's completely possible we have a 5-sided building. Okay, so there would be a fifth row alongside over there. But basically what we want is area of the opaque wall and an estimate of the U. The U values in standard U values are for wall, windows, and roof and floor. Okay, I literally missed. Also, we'll consider the windows over there. That's also important. We can't miss windows. So we want to take the glass area, because that's also included in the conduction load. The glass area. So for walls, for windows, area of window, will be there. Then U value of wall, U of window, and all things should come up. And then basically what we'll do, we'll just multiply U of wall and U of A of wall and the delta T. Delta T is going to be constant because that's the outside temperature, which is constant depending on the weather. Inside temperature is constant depending on the measurements I do. And then in the next column, I can figure out the U into A into delta T for each of these orientations, then sum up at the bottom over there. And that's my total Q, right? And that's how we can figure out the amount of transmission load from windows, walls, floor, and roof, because all of this will have U into A value specifically. Now, to consider for the infiltration part, we need to consider a little bit different thing. And let's go into the U. For that, the U value, like overall heat transfer coefficient, is not explicitly available for infiltration. So how do we figure out the U into A for infiltration? So the U into A for infiltration is going to be rho into V dot into Cp, where rho is the density of air. Let's just write over there. V is the supply flow rate in building, and Cp is again specific heat of air, and this is the density of air, just to mention it as it is. So I hope I have given the basic idea. In the next video, we'll go into the numbers. Now we'll go and actually solve for one of the a building use case, and see what are the values of U, A, delta T, and Q coming, to give us a basic idea of what the transmission load is due to conduction from these all different factors. And then we can figure out what value is so small, so we can ignore in that value from the further calculations, and which value is higher. We'll get the basic idea. So that's all we have. Thank you.